All right, so this module is going to be about network communication devices. Just real quick, I'm going to skip right through this section here. Give me just a second. This week there's no labs or anything for this particular section, so the activities are going to be the videos that you guys will see inside of your Netacad section, and then you'll also have some check your understandings as you go through that material as well. But there won't be any labs associated with this particular module. Okay. So for network communication devices, most of you guys are familiar with this. They're often referred to as end devices. This is going to be your, laptop, desktop, phone, printers, phones. Let's see what else you got. Cameras, that kind of thing. Those are all described or associated as end devices. To typically distinguish between those, each one has its own address, as everyone knows. Usually you have some form of IP address, and then you're also going to have different MAC addresses as well. So with routers are going to be devices that operate at layer 3 at the OSI network. So what this is going to describe is this is what's going to interconnect generally more than one network of different subnets. So they are dividing lines between subnets, so to speak. So as you can see in this particular graphic here, you're going to have several routers that do several networks. For example, your home office is out here. You may have a wireless access point with a bunch of devices, and this is going to function as your router, and that router is then going to connect up to the internet. And then you also have routers out here in the internet side. You usually have some form of a router at the outside of a central office or a branch office, and that will connect down to switches that then interconnect down to, these are going to be your layer 3 switches that then connect down to your access layer switches and on into other devices, depending on how large the branch or corporate networks are going to be. So the ideas behind routers is that they're going to use different routing tables and protocols, algorithms, etc. to find the best path to get that IP packet from your home office through the internet or through the cloud and then down to your central and branch offices. There's a bunch of different routing protocols that we will cover and things that you will see, but the idea is that it's going to be, there's different levels of efficiency within those routing protocols. So some are going to be very efficient at certain types of traffic, others will be efficient at other different types of traffic. They primarily have two functions. One's going to be path determination, which is where it's going to determine what is the best path through the network, as well as just general packet forwarding. So if it doesn't know what it's going to where it's going, then it's going to go out its default gateway and forward that packet on for somebody else to find out. In this case, somebody else would be an upstream router. So for path determination, each router is going to build and maintain its own routing table, which is known in networks and how to reach them. Some of them are going to be directly connected, like what you see in the graphic over there on the right-hand side. So if you're looking at Cisco routers, you're going to see a C for that connected, which means they're directly connected. The S that you see over there is going to be a static entry. So this is going to be like a default gateway or a static entry into the table that says go here in order to route out to the next section. Now what you see over there on the right hand side is not really using any routing protocols. It's just basically static addressing based on connected networks and the static entry that you see down there highlighted in orange. So that table can either be built manually through statics, or it can be dynamic based on whatever dynamic protocol you use. As you see there, you can have multiple different ones. So you can use IGRP, RIP, EIGRP, OSPF. There's a bunch of different flavors of each one of those there as well. So packet forwarding is generally accomplished by using a switching function, which means it's just going to bring it in one and out the other. That's generally to accept one packet on one interface and forward it out another interface, no different than what your switch typically does. That's to just simply encapsulate packets with the appropriate data link type and then going out the data link to forward that packet on. So after the router has determined the exit interface, then it's going to use path determination. The router must encapsulate that packet into a data link frame, which we know, in order to send it out the wire in this case. Once a packet is received from one network destined for another, the router performs the three major steps, and this is going to be part of your exam. It will de-encapsulate the layer 2 frame header and trailer to expose that layer 3 inner packet. It's going to examine the destination IP address of that IP packet to find the best path within its routing table. And if the router finds a path to the destination, then it's going to re-encapsulate it into a layer 3 packet with a new layer 2 on the outside and forward that frame out the exit interface. So as you work through your layers, you can think of it as an onion. It starts on the outside layer, which is going to be your layer 1. This is what's actually sending the ones and zeros on the network. You're going to get into layer 2, which is going to deal with your MAC addresses. Here's where I'm originating. Here's what I want to get to. Inside of that is going to be layer 3, which is all your IP address and routing information. Further in, you're going to be dealing with the other layers, but primarily the data packet, right? This is whatever data you're sending up. So whether that's associated with an application or maybe it's just a datagram going through the network, that all doesn't matter. We're really concerned with layer 2, layer 3. So just like we talked about here, you're going to have layer 7 all the way down through 3. Through 1, it's going to send that packet out. The router is just going to go up to layer 3 to figure out what IP address it needs to get to, then re-encapsulate it, send it over to this one based on the 2 MAC addresses that end here, goes back up, and then it will de-encrypt that packet over here on this router, then go through here, reassign the MAC addresses on these serial links to know what interfaces to send them out, and then keep going through until it's reassembled over here back on the PC itself. And then those layers are peeled away in order to get the data up to layer 7. So on the packet forwarding decision process, this is what a router will do in order to figure out where it's going to send things. Again, it's going to take off that data link layer header. This is the layer 2 stuff. It's going to find the destination IP address, then send it over to the routing table. Once it looks in the routing table, you generally have a bunch of prefixes and the links of those. It's going to find one of those entries, and then based on that entry, it's going to determine which path is going to be the best. If it doesn't have any kind of route entry or does not have a default route, then it's just going to send it to the trash. It's not going to do anything with it. You could also do a null route. For example, if you have incoming traffic from a particular network and you do not want to route that traffic, it's going to match that entry and immediately send it onto the trash. This is beneficial if you're getting a bunch of attack traffic from a particular network and it's not something that you need. This is generally on a public network, not on a private IP address space. But on a public network, you can then send that out and drop those packets immediately so that your router is not trying to process those. From there, it's going to go through, find a match. Once it finds a match, it's going to send it down here. And then based on that destination IP address, it's going to say if it's a directly connected network, then it's just going to forward that packet out as just layer 2. In other words, it knows where it's going because it's directly connected to the router itself. If it's not, then it's going to send something out to the remote network based on the next hop router that it has associated in the routing table. So again, there's 3 actions that are going to be performed on that packet based on best path. It's either going to forward that packet to a device on a directly connected network, it's going to forward it to a next hop router, or it drops the packet because there's no match in the routing table. If it forwards the packet to a device on a directly connected network, this route entry indicates that there's an egress interface directly on the router itself. So it could be Ethernet, it could be serial, it could be whatever means of connectivity that it has at the device. It could even be wireless if there's a wireless card within the router. And that means that that destination IP address belongs to the device that is directly connected to the network. That packet can then be forwarded directly onto the destination device and an end device with an Ethernet LAN, which means the packet must be encapsulated in an Ethernet frame. To encapsulate that packet, then the router needs to determine what the destination MAC address is associated with that destination IP address. The process will vary depending on whether it's IPv4 or IPv6. So in IPv4, the router is going to check its ARP table. As we talked about in the previous module, we're going to use ARP for IPv4. With IPv6, we're going to deal with neighbor solicitation messages and then neighbor advertisement messages in order to determine the proper MAC address. If we forward that packet to the next hop router, then we're going to look inside our router entry or the routing table, find out that it's on a remote network, and therefore that means that we're going to have to send that destination IP address of the packet belongs out there, and we're not going to be able to send that directly out. Therefore, we're not going to determine the MAC, but we are going to have to determine the MAC of the next hop router. And so instead of sending it to the end device, we're just going to send it out to the next hop router. And then once it finds that, it'll pull it back and then send it out. And that's generally either in the ARP table or a neighbor cache, and then instead of trying to use the destination IP address. Otherwise, if it is no match, it just drops the packet. So directly connected routes, these are all going to be from active interfaces on the router itself. I think we've iterated that enough. And then remote routes are going to be connected out to other routers. All of this goes into the routing table, which is basically a file inside of RAM on the router. And that's used to store all this route information that's consistently changing. So based on the network and topology, for the most part, once it learns everything in that table, it's fairly consistent. The only thing that would change there is if you have an upstream router that's doing dynamic address resolution, and if it finds that interfaces go down, etc., then it's going to update through the routing protocol, depending on what you're using, OSPF or EIGRP, etc., in order to say that route is no longer valid because of a link loss or something like that. Then it's going to say go out this interface, and it will update the routing tables accordingly. So over here on the left-hand side, you can see this. This is for directly connected networks. If this router is directly connected to this network, it just takes a packet in here, finds that it's directly connected, ships it over, and then sends it out to this other network here. If it is a remote network and it needs to go out this interface, then it will send it over here and go out. Once this router de-encapsulates it, then it's going to go and find the MAC address because it has a directly connected network so that it can send it on to the remote device, end device. So local route interfaces, these are added when an interface is configured and active. This entry should only be displayed in iOS 15 and newer IPv4 routes and all iOS releases for IPv6. You have directly connected interfaces. These are added to the routing table when an interface is configured and active. Again, they're referring primarily to Cisco type routers here, but this would be applicable across all different router types. So if you're using Junipers, etc., you would have the same methodologies that are going to happen on those routers. So these were added to the routes manually, the static routes, and then there's an exit interface. So it just uses what's called the default route for that static route. And then you have a dynamic routing protocol such as EIGRP or SPF where they are learned from other routers. So if you have these configured with other routers, it's going to start sharing certain routing information among all your routers. So one of the first dynamic routing protocols was RIP, and RIP is one of the easiest ones to set up and use. RIP version 1 came out in 1988. That addresses the needs of larger networks for two advanced routing protocols for OSPF, and then as well as ISIS, which is intermediate system to intermediate system. Cisco then developed IGRP and then an enhanced EIGRP or EIGRP, which also scales to even larger network implementations. You usually have BGP or Border Gateway Protocol. That's typically used now between ISPs and their larger client private client information that's routing out there. So if you're at the ISP level, you're going to see a lot of BGP. Even in the higher corporate stuff, you may have some BGP. But inside your larger corporate networks, you're going to see things like IGRP or EIGRP, depending on which protocols you like to run and the equipment that you're running inside. You may also see OSPF at a certain case. And so you can see these different types of protocols. So your exterior ones are going to be your BGP stuff. Link state, which is it's going to be monitoring to find out if a link goes down. So say a fiber got cut, etc. OSPF and ISIS are going to be your link state protocols. And then you have your distance vectors, which is going to be RIP and EIGRP. Those are typically used based on the number of hop counts that you have between you and the farthest router that you're trying to get to. For your end-to-end packet forwarding, so you're going to see what's going on here. You have this video within your module. You'll see how that animates and goes through, particularly for how you forward packets across different routes. As R1 typically forwards that packet over on to try to get to PC2, just like we've described before, it's going to go find the destination MAC address of the router in order to keep re-encapsulating that packet until it works its way across. Other devices besides routers, we have things called hubs, bridges, and LAN switches. So you can see these icons that would describe what those are. An Ethernet hub, most of you probably have never dealt with one, but what it does is it acts as a multi-port repeater. So it receives data in on a port and then immediately generates it out all the other ports. Hubs use a physical layer processing in order to send that forward and forward that data. In other words, they're pretty much dumb hubs. There's no real generation or encapsulation or anything like that going on. It just pulls in a packet, sends it out all the other ports. So these were pretty common back in the day, and this is like the first switch, or in this case, the first hub that I ever had in my home was a hub. So the problem with this is, one, it was back in the 10 MIPS days or 10 meg days, and it generated a lot of traffic, because if you're coming in one port and then forwarding it out to all the other ports, whether they're supposed to get that traffic or not, it's just forwarding that information out. So it's not extremely efficient in that regard as well. So if you're sending a bunch of data from one computer to another, you're more than likely going to get a bunch of collisions within that network, because you're constantly sending one traffic out and pushing a bunch of other ones out. So you have what's called hubs, and those generally go between, or the bridges, and those generally go between hubs in order to divide that into multiple collision domains. So in a collision domain, it can only send one sender at a time, right? So it's trying to prevent collisions inside of there. Therefore, if you can only have one computer communicate at a time, you're not getting any kind of duplexing or anything like that. So switches are basically multi-port bridges so that you have smaller collision domains, and therefore you operate in like a star topology. So switches are a segment on a LAN that separates those collision domains, one for each switch port, and therefore a switch will make forwarding decisions based on the MAC address. So when switches came out, it significantly reduced the chatter, so to speak, that's going across all the wires. It also is extremely more efficient because it will only send the traffic out on the destination that it's designed for. So if I'm wanting to communicate from PCA to PCB in a hub, I'm just blasting it out all the ports that are on that hub. So if it's a 24-port hub, all 24 ports are getting that information. If it's connected to a switch, it's going to start looking at the MAC address and now determining which port it should be forwarding out. If it doesn't know which port to forward it out, then it has a default port that's connected in order to send that traffic out. Generally, it will end up forwarding out all until it gets a response for that particular MAC address. So a switch itself, again, is going to focus on the MAC address of direct network communications within the switch, find out which one it's appropriate, and goes on. So this is commonly called the MAC address table on site of switch, or it could be called a CAM table, content accessible memory, kind of depends on what it is. They're just special types of high-speed searching memory that's available within your switch. It could have a bunch of software that's controlling these. You can determine how to handle those incoming data frames by maintaining that MAC address table. And you can use this information on that MAC address table to send frames destined for specific devices out a specific port. So it's constantly learning MAC addresses connected to that port. So you'll see this when you first pull in and send traffic from PCA. It will say, I don't have this source MAC address in my table. The incoming port is now in there, so it's going to log it. So the first thing it's going to do is PCA is going to send traffic. It comes up to the switch. It says, I've never seen your MAC address before. I'm going to log that inside my switch as you coming into my port 1. And then I'm going to go send out traffic and find out where you're at to where you're destined to send this traffic to. If I have it in my table, I'll do a lookup in here and immediately forward that packet out. If I don't have it in my table, then it's going to go through and try to forward it out all these ports to see if it can get a response back. In this time that it sends this up, this table, you don't want to end up building a static table. And the problem with the building a static table is if an entry is in there for too long, say PCA goes away and you connect a new PC up here into port 1, then you want to make sure that it updates to the new PC's MAC address, but you also don't want to have this MAC address available anymore. It should say I don't have that and start dropping those packets or returning them back to the sender. So typically there is a refresh timer on those entries, and for most part, most Ethernet switches keep that to about 5 minutes. You want this to be as short as possible, but not too short in order to keep that MAC address fresh. The other reason for do this is MAC address poisoning. We talked a little bit about man-in-the-middle attacks, etc. If I poison a switch's MAC address table, it's usually only valid for about that 5-minute period, and then the switch is going to relearn all the MACs, and that keeps everything bad. I then have to repoison back the switch in order to get access to everything. So as we see here, it's going to forward this out because it doesn't have that destination packet, and then it's going to send it out. And then when one of these responds, for example, the other frame here, which they didn't show in there, let's go back, I can show you what it would look like. Once one of these responds, it will then learn that MAC address up here in the switch, and then it will be permanently in the switch for at least 5 minutes or whatever the timer is set to. Okay. We also have what are called VLANs. So for those of you that didn't quite get through Internet Networking 1 yet, VLANs are a way to group devices within a single flat LAN or a single physical network. It provides some segmentation as well as organizational flexibility within the switch network. It allows an administrator to segment those networks based on factors, usually such as like function, a project team, applications, without regard for the physical location of the user. So we don't really care if they're on the first, second, third floor. What we do is we have a switch on each one of these here, and these different groups may be associated with different floors. So VLAN 2 is going to be associated with IT, and they have this subnet, which is the 2.0/24. So they have all 256 IP addresses here. You have the VLAN 3, which is for HR. They're on .3. And then you have .4, which is going to be for VLAN 4. Those are all going to get trunked over this particular wire all the way through here so it can get to the appropriate devices. And then it gets trunked back to this router where it can reroute that traffic. So if I have something come in from IT and it's going to come in on VLAN 2, that traffic's going to come in here and say it's destined for your HR department. It's going to come through here, go down here to get to this MAC or to this router. Once it hits the router, it's going to go back down that wire but be encapsulated for VLAN 3 in order to get over here to the HR department. In order to keep loops, so the last thing that you want, especially it used to happen on hubs, etc., is that you have some kind of loop. And what loops are is where you connect one switch to another. When you're connecting those switches together, if it goes back again from that switch to the other switch, you end up creating a loop. That loop is going to have severe consequences, and what that's going to do is pretty much block all the traffic and send it into a switching frenzy. It's cool to watch. All the lights on every switch will blink in unison. Looks like a lit up Christmas tree, but all your traffic's going to die. You won't be able to transmit anything across there because it's forwarding packets at such a high rate. So typically we use a protocol called spanning tree in order to prevent that from happening. What it does is typically looped into duplicate frames will get addressed with STP in order to find out logical pathing between different switches, and they'll use what's called a BPDU. This is a bridge protocol data unit, and that's used to prevent those loops. So if it determines that, hey, I've got 2 outbound ports that can cause a loop, it's going to shut one of those ports off. Therefore, it's not going to be allowed to send that traffic down both ports and cause it to end up looping back towards you. So the path is ever needed to compensate for a network cable or a failure. So it's nice to have 2 uplinks, right? You have redundancy. With STP, it's going to calculate which one of those it's going to use actively. If that port was to ever die, whether the port went bad or the cable in between went bad, etc., it's going to stop sending that traffic out. STP as a protocol will then come back and say, now use the other port. And then it's going to send that traffic out the other side without you starting to lose traffic. And it generally happens fairly fast, but it depends on the timers that are set. You also have what are multi-layer switches, and this is what I was showing in that data center in their graphic. Layer 3 switches will do everything that a layer 2 switch does, but it also has the ability to forward frames based on layer 3 or layer 4 information. Typically, these are available so that you can almost kind of use them as a router, but you typically only have the ability to do static routing with layer 3 switches. So a pure layer 3 interface is a lot similar to a physical interface on an iOS router. You can usually use any port on the layer 3 switches in order to do routing out. You just have to tell it that it's a routed port. There's usually limitations on the number of routed ports that you can have going out of a router, or in this case, a layer 3 switch. And you can use what are called SVIs or switch virtual interfaces. These are just a VLAN interface used for inter VLAN routing. So typically you would have a router that would be the .1 or the .254 of a given VLAN. That way it can route that traffic. And that, like I said, has to go clear down to the router and then back up. Well, if you have SVIs on those individual layer 3 switches, then it doesn't have to route clear down to the router. It can actually determine at the local switch level and resend that back out the floor. That keeps the traffic from having to go all the way down like we described in that other photo. So like here, you're going to see these are typically the symbol that's used for a layer 3 switch. This would be a layer 2 switch that you see here. And then these two PCs are on individual VLANs. If it comes up to this switch, it can't route that traffic over, right? It knows that it's on a totally different IP network. And so it's going to come up here and then hit one of these two distributed switches, or commonly referred to as the routed switches, layer 3s. Once it finds that network, then it generally has another connection in order to route that back over here to VLAN 20. Now, it may come up and go over and then come back down. You can notice here you have a lot of redundancy within this routed network. So because you have these routed ports, in other words, these trunks going between here and all this cross connectivity, if I was to lose any one of these links, I can get connectivity out a different direction. It's handy, but it also greatly enhances the amount of routing and such like that that you have to have running locally within your switches. So STP, etc., does not work on a routed interface. So STP is only going to work if these are layer 2 network connections. If these are layer 3, then we're not going to determine layer 3 for STP. We'll use routing protocols at that point. That would be something like OSPF or RIP or EIGRP. You do have some protocols called LACP or Ether channel that function at layer 3. Those two protocols, what they are is typically to combine multiple interfaces so that you can send double the traffic across there. So for example, if I have a 1 gig pipe here and a 1 gig pipe here, I can do either LACP or I can do Ether channel in order to bond those two together. Sometimes I can get up to 2 gig worth of throughput here. Or I can have a full send this direction and a full receive this direction so that I can use twice the bandwidth that way as well. There's different ways to configure those protocols. So switch virtual interfaces, as we talked about, again, this would normally have to go up and out here and up and out here. In order to do this on a layer 3 switch, what you can do is create these SVIs with your VLANs in there, and that would allow it to route without having to go clear up to a core router up above. All right, we're going to talk a little bit about wireless communications. You guys will have those videos there. Wireless networks versus wired networks. Most of everybody today has some form of wireless at their home and obviously at the business as well. With so many devices having wireless connectivity, it used to not be as common, and it certainly wasn't as common if you wanted high speed and or reliability. But these days, with the new protocols and the different frequencies that are available, you can do significantly better wireless deployments that rival even wired connections. So wireless LANs are all on the 802 profile, and so you're going to our portfolio. You have 802.3, which is your standard Ethernet, and then you're going to have wireless stuff, which is 802.11. Wireless LANs connect to clients through a wireless access point or a wireless router, depends on what they are. There's a difference between a wireless access point and a wireless router, instead of the Ethernet switch, right? So instead of being directly connected, it's going to connect to one of those two. Your wireless LANs connect like mobile devices, such as your phone, as opposed to being plugged into the LAN devices, so you don't have PoE type interfaces with the wireless. Those NICs tend to reduce the battery life of a mobile device. The hosts itself contend for access on the RF media, so those different frequency bands, and they use different frame format than wired Ethernet frames. They have additional layer 2 information inside of there that tell them which channel and frequency, etc., that are on there. It obviously raises more privacy issues because I can listen in on radio frequencies where, as opposed to having a hardware tap, which a hardware tap only works in certain ways too. But you would have to have physical access inside of a network. You can't just put up a barrier that says no wireless goes beyond this point. Typically, it will stretch outside of the facility, unless you're putting up Faraday cage or something like that that would block the wireless signal. So with wireless LAN, you're going to use a radio frequency versus physical cables. This is the medium that you're using for transmission. With media access on a wireless network, you're going to use collision avoidance, and over here on wired, you're going to use collision detection. So know the difference between those two. With availability, anybody within the wireless NIC's range can have access to the access point. Over here on the wired, you're obviously going to have some kind of physical cable connected in order to get access. You can get signal interference on a wireless network. It's very minimal wireless interference on a wired network. As a matter of fact, today with the different twists and things like that on cabling for Cat 5, Cat 6, etc., signal interference is very minimal. You have to try pretty hard to try to get interference. Running down power lines is about the only way that you can really start to introduce interference. With regulation, there's different regulations by country for the wireless side, and on the hardwired side, you're going to have IEEE standards. So what does this look like? On an 802.11 frame, you're going to see this header information. And this is for the wireless side, so you're going to see frame control. This is going to be setting up your wireless frame. Has different things like protocol information, frame type, address type, all this kind of stuff here. You're going to have duration, which is going to indicate the remaining duration needed to receive the next frame coming through. It's going to contain the MAC address of the receiving, MAC address of the transmitting. For the third one there, it's going to be the MAC address of the destination. And then you're going to have the sequence control, which is here. That's going to set up your fragmented frames, etc. And address 4 is usually missing as it's only used in ad hoc mode. So you have two different versions of wireless. You either have connection from your end device to an access point, or you could have end device to end device, but they can't be communicated with anything other than those two devices, and that's called ad hoc mode. And so this contains the data for the transmission. This is your payload up here. And then your frame check sequence, this is going to be used for layer 2 error control. Let's see, they're talking about CSMA and your CA. So wireless LANs by nature are what's considered half duplex. That just means that only one client can transmit or receive at any point in time. Versus a full duplex, you can have multiple communications going on between your devices. With a shared media, that means all wireless clients can transmit all and receive on the same radio channel. That'll end up causing a problem. And so this is what CMMA or CA is, which is a carrier sense multiple access with collision avoidance. So what this is just a method to determine who can send and receive on a network at any point in time. So a wireless client does do the following. It'll listen on the channel to see if it's idle. If the channel is also called the carrier, so this is your carrier detection that it's talking about before. It's going to send a ready to receive or RTS message, or ready to send, I'm sorry, message to the access point and request dedicated access to the network. If it receives a clear to send message from the access point, granting access there, if that wireless client doesn't ever receive a CTS, it waits a random amount of time before restarting the process. So it doesn't have a set fallback timer. It's just going to be a random amount of time to go check again. After it receives that CTS, it then goes ahead and transmits the data, tells all the other devices on that network to pause. So all transmissions are going to be acknowledged at some point. So as you can see here, you have a wireless client that's going to do a discovery to find out which access points are out there. It will then authenticate with that access point and then associate itself with that access point. In order to do that successful association, a wireless client and AP must agree on a specific set of parameters, and those parameters must be configured on the access point and subsequently on the client as well. So you'll have things like your SSID, which I think most of you guys are familiar with these days. This is going to be the ID or the name of an address that shows up available for connectivity. This could be hidden. You can configure this to be hidden in the SSID. However, if you're listening to all the networks out there, you could still find what's going on. You can still see the MAC address and the preambles and all that kind of stuff going out there. You just don't see the SSIDs as being advertised. You have a password. This is generally required from the wireless client to associate or authenticate with the access point. This could be at different levels of encryption, which we're going to talk about in the security mode. You have a network mode, which is going to be all the different standards that are out there, and there's a lot more now. You have A, B, G, N, and then AC and AD, which is just going to refer to typically the mode which allows different transmission speeds. In your security mode, you're going to see something like WEP or WPA or WPA2. You always want to enable the highest security level that's supported. This is typically done in order to make sure that you can get the best encryption that's going across there, because things like WEP and WPA are generally fairly easy to crack. WPA2 is a little harder in order to get the keys and the addresses for that. Channel settings, this is often referring to frequency bands that are used to transmit the wireless data. So there's different channel sets for each one of these given standards that you see up here. So for example, on B and G, you're going to see things like channels 1 through 11. However, for A and N, you're going to see a whole lot more channels go in between there. So if we look at active mode and passive mode, this is how it's going to connect out to the access point. So your access point is going to send out a beacon, and that's going to contain the SSID, the supported standards it has, as well as the security settings, telling us, you know, I'm using WEP, I'm using WPA, I'm using WPA2, etc. You want to catch these beacons, and these beacons are going to be caught by the clients in order to find out what's available. So in this mode, the access point is openly advertising its service by periodically sending these. It's going to send out, the primary purpose of that is to allow the wireless access points to learn about these wireless networks and that the access points are given those areas. If you have a hidden SSID, that beacon is still going out. It's just that the SSID is not showing up. In active mode, at this point, what's going to happen is your wireless client's going to send a probe request, and then you're going to get a probe response back from the access point itself. So the wireless client initiates the process by broadcasting out a probe request frame on multiple channels, including the SSID. This is typically what's done when your SSID is hidden. You have to configure the client to say, I want this SSID. It's going to have to go out and see if that access point is truly there, and if it is, it will go ahead and get those supported standards back. Active mode is required if the AP is configured not to broadcast those beacon frames, which we talked about. And a wireless client is used to send a probe request without an SSID name to discover nearby access points. So an access point configured to broadcast those beacon frames would respond to the wireless client with a probe response and then provide the SSID. There's a bunch of different wireless devices that are out there. In general, you have a wireless LAN that requires wireless access points, and then clients that have wireless NICs. And usually a home or small business, you're going to have these little wireless routers. You guys are probably familiar with something like these in your home. However, in larger networks, you're going to have what's called access points. And so an access point just typically goes from your Ethernet interface or your wired network, and then translates that over to wireless. So it's not doing any routing function or anything like that. It's just going to be what's considered an access point, converting Ethernet wireless over to, or Ethernet hardwired over to wireless. You generally want to have one or two of these, depending on what the location is, maybe your home or your small business. You may need to have multiple access points in order to get the coverage that you need for your entire perimeter, rather. So of all these, they're all going to control and management functions that are centralized. This is going to be what's called a wireless LAN controller. So if you're on the Cisco side, you will have a router with a wireless LAN controller that then goes out to all these lightweight access points. What's nice about that is the wireless access points aren't configured to act autonomously, which means they're going to act as just real lightweight dummy access points, and they're going to get all their information from up above. Those lightweight access points are then just forwarding data between the wireless LAN and the wireless controller. That controller will determine what's going out there. All your management functions, such as your SSIDs and authentication, etc., is all centralized to the wireless controller versus configuring every single access point. So the main benefit there is just simplified configuration, as well as being able to monitor all these different access points for one period without having to log into each access point and see what's going on. All right, so to summarize what we covered here today, your end devices are going to be what's connected to the ends of your LANs. This could be other LANs that are going through there using an internetwork of intermediary devices such as routers and switches. Routers are the network layer 3 devices, and they use the process of routing to forward data packets from one network to other subnetworks. Routers will provide path determination and packet forwarding services. Switches will segment a LAN into separate collision domains, one for each port. A switch is going to make those forwarding decisions based on one's MAC address and how they're contained within the Ethernet frame. It's going to use the MAC address table or the CAM table in order to do lookups to find out which port to send it out. Switches are configured with spanning tree protocol in order to prevent loop 3 layer 2 by intentionally blocking one of the redundant paths that would cause the loop. A multi-layer switch, also known as a layer 3 switch, not only performs that layer 2 functionality, but it also does the forwarding frame based on layer 3 information. Let's see, a Cisco Catalyst multi-layer switch also supports doing routed ports as well as SVIs, or switched virtual interfaces. This is going to allow you to do routing closer to the switch itself and closer to the device. Wireless networking devices can connect to an access point or a wireless LAN controller using the 802.11 standard, not suing, but using. The 802.11 frame format is standard for Ethernet frames, except it contains additional fields. Wireless devices are going to use what's called CSMA/CA, so carrier sense multiple access. Remember, carrier is just another word for the channel or the frequency that it's being transmitted across, and using collision avoidance to make sure it doesn't send traffic, and it's going to use the different carrier requests and probe response and clear to send, etc., in order to send that information. When you are connecting to a wireless access point or a wireless LAN, it's a 3-stage process. You have to discover the wireless access point, authenticate with it, and then associate yourself with that access point. Access points can be configured autonomously or individually, or by using a wireless LAN controller in order to simplify that configuration and monitoring of numerous access points. And that concludes today on your network connection devices.